sense of some of the others. And that has to do with value objects as a pattern. Value objects are immutable objects. And I'm not going to have time to go over all these lines here. But they're objects that can't be changed. Where recently have we seen value objects? There's a construct in Scala we actually covered that creates immutable objects. And indeed, actually, if you create things as variables in Java, say as formal parameters or as fields, and you don't indicate what they are, say at the top of a class declaration, it will assume they're value objects and therefore immutable within the class. Where else have we seen something in Scala that builds, it actually builds, or it's associated with value, with things that are immutable? Val. Yeah, so we declare things as val. And val indicates that a variable is a nice, it's a name for a value, but it doesn't change over time. In contrast to var, right? So we might have something as simple as pi, with some 3.14159, etc. When I was an undergraduate, I knew someone who knew pi, I think, to several thousand digits, if I remember correctly. Yeah, that's pretty good. Okay. I know fewer, but we could have fun together. But this is kind of a nice little name for a value. And in fact, a lot of the times that we build objects in Scala, we're building objects out of pieces in forms of variables that are immutable. They're value objects, okay? Rather than variables like a counter, right? So count iterations or something where we're actually changing it and counting the number of times we have some iteration. Here we actually will be changing it. It's a variable rather than a value. And indeed, in Scala, there are these things called case classes, which we build up with a particular idea in mind to decompose them, to destructure them, say, in match constructs with unapplied, like we saw last time. And case classes are by default value objects. They're immutable objects. Now, to someone used to old object-oriented sort of chestnuts about classes being places where you store the data, the state of an object, and its methods, it may seem weird to have these value objects. After all, you have getters and you don't have setters. What's the use of that? Well, it turns out it's incredibly useful, and it's more than that. More than being useful on their own terms, they're useful as building blocks. And we'll see why this is, okay? So when we talk about immutability, we're really dealing with the fact that in code, there's changes that often take place. And a lot of the cognitive overhead, a lot of the sort of complexity of code comes from tracing through the changes, where things came from. So, I have this guy, total revenue here, this variable, and it was computed up here. And this thing was first initialized up here at the top. And a lot of what makes code that you're looking at complex to reason through, code in traditional object-oriented or imperative programming, is that you got to trace these dependencies. Where did this guy get initialized? Where was this value set, etc. Okay? And it's one of the things that makes functional programming clearer, because you're writing things in almost an equational way. You create a value, you pass it in as another thing, it returns another thing, you pass it in as an argument to yet another, and the dependencies are clear. What depends on what is more clear. And so, people spend a lot of time trying to simplify the understanding of code like this, to train what I call the dragon of side effects, okay? This fearsome complexity that extend from it. And one of the big attractions of functional languages is those dependencies become clearer. So we just have, say, a call to a function that performs things, and what it depends on is really clear here. And we often will have very simple input-output dependencies of a given function. It depends on certain things to do its value, to do its job, and it returns certain values. And often we even nest these calls. So instead of having total revenue equals array total of this, and then calling normalize array with that as one of the arguments, we instead will have normalize array, the first two arguments, and then we'll just put in this call to array total. We don't even have to have the variable, we'll just put in the call there. And there's trade-offs either way. But the point is that in functional programming, we're often trying to deal with reducing this cognitive complexity that comes from understanding code. What depends on what? It's more clear what normalized array depends on because it's just the arguments that are passed to it. Okay. So I'm not going to have time to go into this in detail, but one of the main ways that we can deal with this complexity is by building objects that can't be modified. So when we're working with an object, we don't have to worry that someone else is doing something to it, and we don't have to worry about where it's last been set, because the only place that it was changed, the only place that it got its values was where it was created. So as long as we know where it was created, we don't have to worry it's gotten updated somewhere along the way and scoured this code for the last update to it. Okay? So these are objects which can't be changed, or to be more precise, they have no externally observable changes associated with them. And it turns out that we have lots of these objects in our languages, right? In language, even as very involving lots of side effects like Java, we see primitive types. You can't change an int. If you have an int, you can add something to it and get back another int, but you can't change the underlying int, or a double, right? And there's a lot of cases where even in languages, in libraries of languages that widely support side effects, widely use them, you'll have immutable objects. An example might be a point. So you have a point in space, and you can add, say, a vector to the point and get another point, but you don't modify that point. They're a complex number. You don't set the imaginary component, perhaps, or the real component. Instead, you just create it with the appropriate component. So you can add complex numbers together, get other complex numbers, but you're not modifying it once you've created it. Similarly with pairs, etc. Okay, so you might have something like this, right? You have in Java, you have a complex number, and you have fields which are marked as fine, right? And you can have essentially getters, things that get components of it, like the real part and the imaginary part, and those just return these values. Okay? What's an advantage of having these as methods rather than directly accessing those values, just as a sanity check? Why not directly access these values?
Because then it's harder to control side effects?
It's harder to control side effects. Someone, in principle, could write to them. Although if they were public final, you could manage it through that. But there's another reason why directly throbbing the underlying variables, directly changing them, tweaking them, or grabbing them, more to the point, I'm sorry, if they're read-only, grabbing them, is not desirable. Why is it? Why do we create methods to grab these rather than just grabbing the name itself? This complex number .rd. Imagine this was public file. Well, amongst other things, it gives us a way to evolve the representation. We might represent this with a real and imaginary component, or we might represent it with a magnitude and a angle component, an angle on the complex plane, for whom that's meaningful. So we can have a complex plane, here's the real component, here's the imaginary component, and we could represent this as so much real, so much imaginary. Or we could represent it as a magnitude, that's the length of this line here, this length, and an angle, theta, in the complex plane. We could choose our own representation. As long as we have functions here, we can have our underlying representation, whatever we want, and just return the appropriate values for these functions. So we could calculate them rather than just returning a value. Here we just return the value of a variable, but maybe in the future we want to represent it in polar coordinates like this or what have you, and we want to do a calculation and compute the real part. The point is we have greater flexibility if we're accessing it through methods. Does that make sense? In other words, we can change names of these. We can change how it's represented, what information we store, actually. And we can go from a situation where maybe in the original version of the class we're just returning the value of a field to a situation where we're actually performing a calculation and using that to return the value. We have a cleverer way of representing it. So providing these accessors, these getters, as it were, has some real value. It's not just, you know, adhering to the to a ritual of only providing these things. The other thing is, at a more conceptual level, you don't want to be depending on the underlying representation, because the underlying representation will often evolve, and you might want ultimately to have a interface, a specification contract for this, and that won't depend on the underlying representation. It will depend on what's captured through methods. Anyway, this is a class, a value object class. Once it's created, here's the constructor. Once it's created, we never change it. You can get its pieces, you can add them, you can subtract them and multiply them, but when you do these last few operations, what comes out is a new object. You're not modifying this object, right? Hence fine. Does that make sense? Are we on the same page here? Okay. Okay. Somehow I seem more excited about it than you do. That's okay. That's nothing new, right? Okay, so why do we build these things? Well, they simplify our reasoning. We don't have to worry that someone's updated it before we get it. Once we get the values, once we've gotten the real values by, say, calling real part and using them in some variable, you know, we're using a complex number, we ask for the real part, and then we're counting on it. We don't have to worry someone's updated it in the meantime, right? And this is kind of nice. We know if we call it once and we call it later, we'll get the same value back. It's a pure function. But one of the biggest reasons is it's easier to incorporate as a building block. Okay? And it turns out that it allows for efficiencies. Having the dependencies be clearer and less tight allows for exploitation of parallel implementations. And I noted this before. I think it was in this class where with a value object, for example, if we have some value object and another one depends on it, it can simply reuse some of its implementation. We don't have to be scared of the fact that, you know, initially we have something that's appended to the distinct condition. We don't have to worry that this is going to be updated later. Instead, we can simply, if we have one string appended to another, we could string them together in this way. So we have pre-condition as two strings that are strung together. If this guy were mutable, if this latter string were mutable, it could be modified out from under us, and we'd have to make a full copy of it, because it could be modified later. But if it's immutable, if this string is immutable, as it is in Java, we don't have to worry about that, and therefore we can reuse it. We can just have a reference to it, to append something to it. Does that make sense? The idea is, if we append one thing to another, rather than making a complete copy of the thing we're appending it to, for the appended thing, we can just reuse a reference to the thing to which we've appended it, because we're confident it will never change. We don't have to worry someone will change it later and then it will change both objects. Okay? And I mentioned the same thing with big nums. You know, if we have an immutable object, we have a plus version, we have a minus version, they can share the same representation because the underlying representation won't change. It's some number. It's not going to change out from under us. Okay. Now, in terms of Liskov substitution principle, turns out if you have value objects, it's much easier to reason about correctness of subtyping. Okay? So remember the Liskov substitution principle. We talked about a number of requirements to adhere to it. It's about safe subtyping. If we have a supertype, we want to create subtypes that won't break code, that knows only about the supertype. And here, we will often think about the preconditions and postconditions of methods and the invariance and history properties associated with a class. The invariants are things that are true at any one time, and value objects need them just as much as mutable objects. preconditions and postconditions we still need to reason about. But a history property here is particularly simple. It doesn't change. We never change the object in a visible way. And as a result, there's fewer postconditions to worry about. The postconditions involve return values, not changes to the underlying object. We call a method. It doesn't change the underlying object in any visible way. So the postconditions are simpler. They just have to do with what you return. And, ladies and gentlemen, moreover, if we have a subtype, that has to remain immutable too. We can't have a supertype that's immutable, that's unchangeable, and then a subtype that's changeable, or else someone could be rudely surprised. They're using it as if it's a supertype, they're counting on all those properties, that it's immutable, and suddenly it's changed out from under them. So if we have a supertype string in Java, we can't create a subtype of string that's mutable and expect the code that knows only about regular strings to still work. Okay, we will be maybe assuming what the third character is of the string, that it will never change. So in short, if we're building things with subtyping, we have fewer things to worry about. We know we need to maintain an immutable object for a subtype if we have an immutable object for a supertype, and for postconditions it's easier to reason about. And with invariance, if they start true at the time of the constructor, they will remain true. We don't have to worry about rechecking them on an ongoing basis. Is it still true? Am I still sane? Am I still sane? I'll ask you. This is something we don't have to keep on checking. We check it once at the constructor, and we're done. Okay. Okay. Now let's talk about immutability, and this has to do with the. If we think about how to capture this, it'll clue you into how you can achieve it in Java. There's really two ways. One thing is, just like the class we saw a few minutes ago, the complex numbers class, we make all fields final. So we do this. We make them final, and then we go and make all methods perform no side effects. We don't allow overriding, so we have final versions of the methods so that they can't be overridden, for example. And we don't have any. We don't give out any references to internal data structures we're using that are mutable. Okay. And here, we're guaranteed to have, if we don't allow overriding, we're guaranteed that all subtypes are also immutable. Of course, you can allow for overriding by not having final methods, but then you're counting on subtypes needing to be immutable. And you want to document that you're counting on that. So here, ladies and gentlemen, we have these fairly clear considerations. All fields should be final. We don't provide any side effects in our methods. But there's this final one that's a little bit more subtle. If we're building our system out of things that are mutable, like dates, we need to make sure that we're not giving them out in a way that will be modified. And this has to do with this whole thing about building objects out of mutable or immutable pieces, and why building them out of immutable pieces is simpler. Okay, so this is kind of a point of reference we'll be considering. This is from Effective Java by Block, which is a great book. It's now in its second edition. Maybe it's going to be coming out with a third edition soon. But it's a fantastic book for those who are really interested in software engineering and Java. So, ladies and gentlemen, here we have a period, something that's representing an interval of time. And in order to represent that, we have a date that has a start and a date and an end. And this looks, by all appearances, like a value object. Why do I say that? Putting aside this consideration about date, why does this look like a value object? Well, let's go through those criteria just a minute ago, right? Are all fields final here? These two fields are final. Okay. Do we have any side effect performing methods? Do any of these methods start and end perform a side effect? Do they change the underlying structure in a visible way? No, they just return these fields. Okay, so we're doing pretty well as far as our checklist. Don't allow overriding. Well, we haven't done that, so we're not fully adhering to it. But it's really the problem I want to draw attention to is this last one. Okay, it's this issue of these mutable fields. So this is mutable. Okay, so what are the problems with this as a supposedly immutable class? Let's suppose we put aside this issue about not allowing overriding, which is it's a stricter criteria yet, not even allowing our subtypes to override our methods at all. If we put that aside and we just consider this issue of start and end being made out of mutable pieces, date is a mutable class, it can be changed once you have a date. What are the vulnerabilities of this class that make it not fully immutable? In other words, that allow it to still be modified. I would claim to you, I would argue to you that this class is not fully immutable. It can be changed. Why?
What does compare to do?
It basically is comparing the two dates to see if one date is greater than another. So start compared to end is asking, is start after end, before end, or the same as end? In this case, start dot compared to end greater than 0 would suggest that start comes after end, and it's flagging that as an error. It's throwing an exception. It's saying basically, hey, you told me to create a nonsensical interval of time where the start is after the end. That doesn't make sense, go figure. So this is throwing an exception here that the invariant has been violated. So the idea is it has some invariant, which is not documented well here, well, here it is. Start, beginning of the period, and the end of the period must not precede start. See that? So they're just checking that invariant. And again, with a immutable class, you just check it once at time of constructor. You're done. Can't be modified from now on. If it's true now, it's going to be true on an ongoing basis. So what's the vulnerability? I would argue this class is not truly immutable. Even putting aside subtyping. Why?
You can get a reference to the date and then just use it.
You can get a reference to the date, and you could use it to print it out or something, but you're thinking about what, Josh?
Modify it.
You could modify it. You could say, hey, give me your start. Okay. Returns start, right? Returns whatever is referred to by the start field. Returns back a reference to that thing. And then the thing that requests it says, thank you very much. I'm now going to set it to be, 496 AD. The collapse of Rome under the Visigoths, or what have you. And suddenly, ladies and gentlemen, you have changed the date out from under it. It gave you back, at face value, it gave you back at start, but now you've changed it. So this period has suddenly changed. It made my appearances seem like a value class, but it's vulnerable. This may be a final reference. The reference doesn't change, but you've changed the thing it's referencing. So here, start, you construct this class, and start points to some value, some date. This is a date here, and this date has some value in here. And you never change what it refers to, but I should be careful about how I say that. You never change the object to which it refers. It's referring to the same object. It's just you're modifying this object. You're stomping on it. You're writing things to it. And suddenly you've changed this period. You haven't changed which thing it refers to. It's just you haven't changed which one it refers to, but the thing it refers to has been modified. Okay, does that make sense? So that's one vulnerability. There's another vulnerability too. Okay, so suppose that we how could we deal with that? How could we deal with this vulnerability? Reduce this vulnerability that once I return start or return end, someone can modify those. What could I do?
Return a clone of the object?
I could return a clone. Make a complete copy of that, right? Okay, so suppose we were to do that. Is the problem fixed? Is there still a vulnerability? So suppose now I said, instead of return start, I said return start.const and return end.const. Turns out there's two vulnerabilities still remaining. One of them is a more glaring vulnerability.
So about all those public non-final methods.
Sorry?
About all those public
Yeah.
non-final methods. Is there any chance that one of them could be overridden?
Yes, there is. And with overriding, you could make something that is a subtype of period that is mutable. That is true. The public non-final methods. That is true.
You said it to be a final class.
But that's true. It's a final class. Thank you. Man, that's greater. Yeah, it's a final class. So you're not allowed to extend that. Thank you for highlighting that. Okay? Yeah. So you can't actually override that. So what's still the vulnerability? I would argue there's still a vulnerability. There's still two vulnerabilities.
In the constructor, you don't make clones for anything.
Yeah, so I could pass in, if I'm creating a new period, I could pass in this date and this other date. I pass in the references to them, right? I tell it, hey, when I create the period, I have a reference to this externally. I set it up. I create a new date for the start, new date for the finish, and then I pass those into the constructor. I say, give me a new period with this being the start and this being the end. And it goes off happily and sets its instance variables to refer to those. But I still may have a reference externally. Your name again? Hi. So I still have a reference externally to them. So I called off new period with this start and this end. I still have a reference to start externally. And after this is created, I can modify that. Suddenly I'm modifying start. Now, that's distressing for two reasons. It's distressing, number one, because now you've changed the period after you created it, which it's not supposed to do. But number two, the period isn't even aware that it's been changed, right? You're changing it out from under it with both methods. That's a distressing thing about this being vulnerable to these changes, either through this accessor vulnerability that we said we could clone, but also, ladies and gentlemen, by passing in a pre-existing reference, which is then changed, it can't then check its invariant. Here, the invariant is being checked when it gets created. It thinks, okay, I don't have to check it again, right? Never have to check it again. But you could be, at any point, you could modify what you passed in, the start, and you could change it, and it doesn't know to check this invariant. And so now its invariant could be totally screwed up. You could have set start to be after the day after end, and it's not going to know about it. It's not going to know its invariant has been violated. That's the distressing thing about building this out of these mutable pieces. It's got these vulnerabilities, and it can't even check its own invariant because it can change without notifying. You see what I mean here? The person who's changing start as a reference to start externally may change it and not even notify period, hey, something's changed. And so suddenly it's going around with a situation where start is after end and it doesn't even know that. And that is disturbing. Now you've sort of changed its internal. So how can we plug the vulnerability with the constructor? Well, turns out it's just along the lines that Josh mentioned. What can we do?
You clone
Clone it. You can clone it. You can clone it. So it turns out there's cloning mechanisms, but you got to even be careful about this cloning mechanism. Okay, so ladies and gentlemen, this is an illustration of the constructor vulnerability. So here I create start and end. I create a new period, and after I created it, I set the start to year 78. What was that? And Trajan's realm in Rome or something like that. I set it its value. So here I've changed the period after I've created it because I still have a reference to end, right? And alternatively, this is the accessor vulnerability. I get the end and I set the year like that. So let's try to clone it. Let's try to deal with this constructor vulnerability, okay? One idea would be to do this, okay? We compare the two values, and then we clone them, and then we're off to the races. Since we clone them, we have now internal variables that are based on clones of these, and we don't have to worry that someone will modify it. What's the problem with this? Particularly thinking about multi-threading.
There's a chance that it was changed while you were checking the data.
Yeah, so it could technically, and believe me, if you work with concurrent systems with large numbers of users and bursty traffic, things get slow. You know, code executes slow sometimes because of cache effects and memory that has to be paged in from disk. So you could have just checked this, verified it's true, and you've just fallen down to do this assignment. You haven't yet cloned end, and suddenly end is modified by the user, by some other thread. It's modified out. So it checked this, and this was true earlier, but then before you get down to this clone, end is changed again to point to 78 and year 78. Now you're in bad shape. Okay. So there's a race condition here. It could be that you do this check, and this check is true now. This is the invariant. Is the start before the end? And even though it's true now, by the time you get down to clone it, it's no longer true. But you've already committed to cloning it, and you clone something that's nonsensical. So, one idea here would be to clone before this check. So you clone them here before you do the check. Now you've got clones of them, and they can't be modified, and then you do the check. Fair bit of work. You're doing this clone even before you do this check as to whether they're meaningful, but it works. You've eliminated this race condition vulnerability, this case where, just as you're starting to clone these here, they've been modified. And it's because it's after this check is concerned, you don't catch the fact that the invariant is now modified. Okay, so that would work. There is another vulnerability, and if we're dealing with security-related things, this is an indication of how deep your extra reasoning has to be. If someone's trying to break your code, spy in the internals of your data structure, they could still deal with that. So in other words, they could pass in something that's a subtype of date where clone is actually overridden to do nothing. It just returns back a reference to the current instance. So you clone it here. Maybe you clone it, but actually secretly you're just getting back an instance to start, which they have a reference to, and they can see internally what's going on for you. So in other words, you're not guaranteed to get back a sort of legitimate clone. So one thing you can do to lower that vulnerability is you actually create a date that's based on the original date. So instead of calling clone, which could be overridden in a malicious way, you instead create a new date. You create a new date based on the older dates, and this is kind of a manual clone. But it's one where you know what class it is. If you're calling clone here, you don't know for sure what class start really is. And if you're dealing with potentially malicious code, this could be used to override clone in a malicious way. Often we're not dealing with worries at that level of security, but you should be aware that there is some code where you have to think about this. And certainly, if you're doing work as a Java virtual machine creator, you're going to need to be worried about surviving in a very ugly internet. Okay, so ladies and gentlemen, for the constructor vulnerability, we can get around it by something like this. We can first essentially clone them. Functionally we clone them. We create new objects, and then we compare them. For the accessor vulnerability, we clone them like this, just like Josh suggested. Okay, so we create these defensive copies. Just in case someone might modify them, we create these extra copies of things. Okay, and We do so when we pass objects in, namely here the constructor. We end up doing this clone. When we pass things in, we can't just, instead of doing this, just putting them directly as references internally, we have to make copies. And when we pass things out, we do the same thing. We make a copy here. Does that make sense? Do you have a sense of why this is? Right? If I'm passing out start, because this is a reference to a mutable object, to a date which can be modified by somebody, if I pass this out, they may modify it without even telling me, without even the courtesy of letting me know. Suddenly they've set my start to be the day after my end. And then it's game over for my invariants. They're out the window. I can't guarantee my properties. They haven't even told me that it changed, and they've changed it. Maybe they didn't even know I was depending on it, right? Okay, so ladies and gentlemen, here we have to make copies of mutable objects in and out. And the basic deal here is, ladies and gentlemen, we're doing a lot of extra work just because there's one stinking reason. Because we're building it out of mutable pieces. We're building this thing out of pieces that are mutable. Now, let me ask this. Okay, so you may say, no, the problem is actually not. So someone could be excused for saying, all this extra work, this extra clone here, all this extra cloning here, and in fact going beyond cloning, really you can go beyond cloning here if you're really concerned about security. You could say, actually, the reason you have to do this, it's not the fault of building out of mutable objects, it's the fact is you're trying to build an immutable object. Maybe we should avoid building immutable objects, they're too hard. Why is that not an answer? Suppose we were not building an immutable object. We don't actually care about point as an immutable object. Suppose we are perfectly happy if point is, period. Suppose we are perfectly happy if this could change out from under us. Suppose we don't want to guarantee, immutability. Suppose we put that aside and say, immutable objects are too hard to build. We have to go through all this extra work for their internals. We'll just have this be a mutable period. Why is that not the answer?
Because that only introduces more overhead, because now you have to start locking variables and checking for acceptances.
Exactly. Now we've got a whole lot of other needs that suddenly come up. We've got to deal with thread-safe versions of this, so that if multiple threads are using this, now we have to kind of broker the connections, synchronize things so that one thread isn't overwriting it, so it isn't halfway through overwriting it while another one reads it. We need to put in place a lot of mechanisms to make sure that this is safe under concurrency. But even more fundamentally than that, ladies and gentlemen, when we build a data structure, we would need to maintain invariance, right? Often we need to say, look, we want our hash table maintained internally to have all non-null keys. We want to make sure that this array that we store internally is not empty. We want to make sure that the certain instance variables internally are not null. We want to make sure that start is before end, or no later than end. Right? Often, regardless of whether it's an immutable data structure or a mutable data structure, there are certain properties, certain invariants, and in fact history properties that we want to adhere to. Right? We want our internal class to be able to guarantee certain things for our algorithms to work. Right? We don't want someone to be able to go in and frob our internal data structures so that suddenly our hash table has a lot of duplicate entries. Our dictionary is suddenly wiped clean or something like that. So in general, when you're building an object, now I don't care whether it's a mutable or immutable object, you want certain guarantees to be maintained. You want to be able to be in a sane state at any one time. And if you are building a immutable object, an object that cannot be changed, it's easier to check those properties. You check them at the time of construction, and if they're true then, they're true on an ongoing basis. If you're building a mutable object, you need to check them on an ongoing basis. So not only do you have to put in place the synchronization mechanisms to which Eric was referring, not only do you have to put in place all this extra machinery to allow this to be a mutable object safely in the presence of concurrency, you also now need to go beyond just checking invariance at time of constructor, and you need to check them every time it's changed. And that, ladies and gentlemen, is exactly the point. You need to know when this changes. You want to check this invariant. Is start no later than end? You want to check that every time it changes. And if you're giving out willy-nilly references to your internals that are mutable, you have forfeited the ability to check your conditions whenever they change, because you don't know when they change. If you give out start, I don't care if period is mutable. We could call this mutable period. If you're giving out start here, someone could modify it externally, and they're not going to tell you. Yes?
Can you use an aspect to tell you whenever one of your variables gets changed?
Yes, you could. With aspect-oriented programming, you could do it. And that's a great example. So, Robert? Tom. Sorry, Tom. Yeah, so Tom's exactly right. So you could use an aspect to look when your field has been assigned, and you could, in principle, say, warning, this has been assigned to. What you couldn't do so easily is check if. So look, this is giving out a date, right? And that date is itself have lots of internal pieces which might be modified. And you'd have to write quite an aspect to spot any place, any of those internal pieces of the date has been changed. I guess you could do it, but it would require a fair bit of aspect-oriented mechanism to put in place that guarantee, right? So what I'm saying is that regardless of whether period is mutable or immutable, you've got to go through this work. If you're building something, if you're building a period, regardless of whether it's mutable or immutable, out of pieces that are mutable, you have to go through extra work to avoid handing them out in a way that could allow for violation of your invariance without you knowing. It may be aspects you put into place. It's true. You could do a neat job, and I love that idea, Tom. Or it might be in the form of cloning them. But the fact is you have to do extra work. So if you're building a mutable data structure out of mutable parts, you're doing more work. If you're building an immutable data structure out of mutable parts, you're doing more work. In short, if you are building something out of mutable pieces, there is more work to be done. And hence, building things out of immutable pieces needs to be considered more carefully, because it involves considerably less work, considerably less vulnerabilities. If date were immutable, if we had an immutable date, would this be okay? Yeah. We return a reference to it, to its start and end. We just check one time. Is the invariant true? We could return a reference to start, or return a reference to end. We could take in references to immutable date and end as an immutable date. And we don't have to worry someone's going to modify them, because they can't be modified. They're immutable. Building things out of immutable parts is easier than building out of mutable parts. Does that make sense? If you're building out of mutable parts, a lot more mechanisms are required. If you are building a mutable data structure, if you're building a mutable class, mutable abstraction, you have to go through more work to deal with thread synchronization issues as well. So in short, ladies and gentlemen, value objects can give us greater clarity in terms of our code. We don't have to worry this thing is being changed somewhere along the lines of this code. If we know where it was at the constructor, we know it's guaranteed to be the same, and we can build things out of it more easily. I mean, if you're building a library and you provide value objects, you'll be confident that those can be used as building blocks with greater ease than if you're providing mutable structures. Okay? Make sense? Okay. So that's value objects. And you'll hear me expound it in greater detail in other lectures. Let me just